recording. All right. And the recorded video will be shared. Those who have already taken up the course, the recorded video will be uh, available in learning management system. Those who are just attending the first session, the recorded video will be emailed to them. The presentation will be shared. In these sessions, you can ask your question by typing while instructor can speak. All right. All right. So in today's session, we will talk about big data and Hadoop. Before that, let me introduce a little bit and tell you a little bit more about no big data. All right. So the no big data is, as an organization, we believe in expert instructors. The main reason why we started no big data, because we realize that in an advanced technology domain there is a gap, industry gap between, and the good instructors were not available. Most of the instructors that those were available has very less practical experience. That is the reason we started no big data. And we have something called cloud labs, which is similar to what you have in organization. I come from Amazon's background. The way at Amazon we were provided with a lab where we can all log in and start working, in the similar fashion I have also set up cloud labs. We provide a lifetime access to learning management system where you have presentations, class recordings, assignments plus quizzes, and the project work available. Those you have already signed up, they can see this. In case you have not enrolled for the full class, you can still register on our website, and under your courses you will see Java course, because Java course is free for all, so we provide that. Now under Java course you can see that the all of these things are available except for assignments and quizzes. There were not many assignment and quizzes for Java course. All right. So next is we provide a real life project to those who finish up our all the quiz assignments and a pre-assigned project. Okay. We provide a course completion certificate. Our support is 24 by 7, and we all right, all right. So looks like okay. So my voice seems to be distorted again for some reason. So I'll try to use another net connection there. All right, all right. So is it clear now? In case it gets distorted again, we will use another connection. Okay. Yeah. So we have something called No Big Data Alumni, where we keep on posting our jobs, which our knowledge partners share with us, as well as we keep on informing you about the latest technologies. Along with that, we try to be connected with our students. All right. All right. So if you have not introduced yourself, please feel free to do so. Okay. So we have Ravidas, who is in Nielsen and Coop, and Piyush Patel, who is from CSC. Good. Yes, Vikas. Nitika has joined. All right. So I'm reading out the questions. All right. Now, So feel free to introduce yourself. So this is a little bit about myself. I'm Sandeep Giri. I'll be the instructor for this course. I did my graduation from IIT Roorkee in 2002, and if in just after college, I joined a company called DE Shaw. In case you are not aware, DE Shaw is into financial services. All right, and at DE Shaw, we actually built and used big data system even before the term was coined. All right. We were actually dealing with terabytes of data in 2002 when other people were yet to discover utilize gigabytes of data properly. So after DESHA, I founded a company called Tbits Global where we built a document management system. And afterwards, I joined in Mobi, where we built a recommender churning around 200 terabytes of data, and also built high throughput analytics system. At Amazon, we built high throughput system for Amazon.com website using an in-house NoSQL. All right. So that is about myself. Let me read out. So we have Chidambaram or Chidu from Infosys, and welcome Chidambaram. We have Renia from Jeddah, and we have Devender who is working at HCL and he's working on cloud and virtualization. Welcome Devender. So okay, we have Harshal. Harshal Shah is from Los Angeles and say hi to everyone. I'm working with India Mart. We have Vikas Goyal who is working with IndiaMart.com as senior product manager, and we have Konkan from he's a he's studying he's studying as database specialist as at North Virginia Community College. Great Konkan to have you in the session. We will definitely have a good discussion and we look forward to great questions from you. We have Sanjay. Sanjay has background in healthcare industry, looking to analyze big data sets to improve clinical care and operations for hospitals and health management. Great, Sanjay. It's really nice to know you because that's a domain which has got a huge potential of big data as well as in general. Okay, so so okay. Thank you, Kronkan. So his nickname is Pop, so I'll call him Pop instead. That will be easy for me. Uh, I am Sweta from Sintel and he's a Java developer. Hello, Sweta. Welcome to the session. We have Nalini from UAE, used to work with YouGov, a MR company. Great. Great to have you in the session, Nalini. Good. We have great set of candidate in the session and from all backgrounds, and I'm actually very happy to have such a great audience. All right. Today, out of 11 sessions, this is the first session, and we are going to discuss general things about big data, then a little bit about uh, Hadoop architecture, and then we'll talk about HDFS. All right. So the session is going to be very interactive, so feel free to ask questions even in the middle of something. Do not wait for me to finish. You can ask question. I'll finish and then answer your questions. All right. We have Srinivas Murthy. He's teaching at PES University at Bangalore. Welcome, Srinivas, and I will look forward to have great questions from you. And even offline, we can have the discussion or meet up sometime. All right. Now, Welcome, sir. All right. So before I start the session, my question to you is, what exactly do you understand by big data? Okay. So let me have a quick answers from you, and then I will describe in my way. All right. So what is it that you understand by big data? Forget the definition. Forget the standard definition. What is it that you understand by big data so far? Nitika says lots of data. Vivek says lots of data, organized or unorganized. Piyush, lots of organized and organized data. Vikas says amount of data that existing systems can handle. Good, good. Nalini says volumes of data. Good. Rania says huge volumes of data from different sources. Malvika says large amounts of unstructured data that needs some kind of processing to infer useful. Great, excellent. Vikas says any data set which is difficult to churn by machine is big data. By a machine. That's a very good point. Thank you, Vikas. Good, good. And we have Sanjay says large volumes of data that cannot be managed through traditional data warehouses. Good. Volumes of data in different format. Chidambar says lots of data which cannot hold in one machine. Good. Lots of data from many sources. The pop says lots of data from many sources. And Rania says that need a technology to handle. Good, good. Very good set of answers. Ravida says high volume, velocity, and variety. Good. All right. So yes. So most of you have already answered pretty well. Let me just summarize what you have just answered. Simply the data of very big size. So when we say big data does not mean technology. Big data does not mean tools. Big data means data of very big size that you cannot process with usual tools, and for that you require distributed architecture. All right. The data can be structured or unstructured. So out of 4 points, the third point is the most important one. Why? Because that is the most concrete definition. So any processing requirement, any churning requirement, if you realize that you need a distributed architecture, you say that your data is big. You are solving a big data problem. All right. So because why I say that the point number three is the most valid attribute of big data, because point one, data of very big size. You might ask how big, can we give a number? Second is can't process with usual tools. What does it mean by usual tools? Does usual tools mean, so generally when we say this sentence, usual tools mean your normal file systems, your Oracle database, your MS SQL database, and all others in the same bucket. But usual tools today, if Hadoop becomes usual tools, can we start saying that the big data which we called big data is no longer big data? So that is why any processing requirement, any data churning need, when it requires distributed architecture, we call that we are handling big data. All right, it's as simple as that. All right. So the voice was distorted for Nitika. Is anybody else also facing the same issue? Okay. So I'm switching to a wireless network. So let me know in case this is better. Hello. Hello. Yeah. Can you hear me now? Is it better or worse? Hello. So, hi, can you hear me now? Can't hear? All right. So, is it better than the previous one, or is it worse? All right. So I'm on a 4G network, wireless one. So let's see if it is better. Good. Good. All right. Now we have now we talked about distributed architecture. What does it mean by distributed architecture? All right. A distributed architecture means getting your work done via a multitude of computers simultaneously. You form the group of net computers which are networked together. They can interact with each other and they all achieve the same goal. Yeah. So Nitika's question was, what does it mean by usual tools? Usual tools means your normal file systems and your databases, usual databases such as MS SQL, Oracle, and others. Looks like people are still facing the voice breaking issue. Just give me a second if I can solve it a little bit. Yeah. So other in this particular thing, this go to webinar, you cannot see the other people's question, but the tool which we'll be using in the next session onwards will be go to meeting, and there you can see each other's question. All right. All right. So Piyush's question is, does Cognos come under usual tools? Yes, it does. Okay. Any non-distributed architecture system is generally we consider non-big data system. All right. All right. So moving ahead. So there are always a confusion about what is distributed and what is parallel. So there are two kinds of computing we generally study. One is distributed. Yeah. So, question, Nitika wants to repeat the question. So, does Cognos come under usual tool? So, my answer is that Cognos does not come under. It does come under usual tools. Is not a big data system. Reason being, any system which handles the data in a distributed manner, we call it big data solution or big data product. And if the solution is not distributed architecture, we generally call it usual tools. All right. So that is why in the whole definition we focus a lot on distributed architecture. The whole game is about distributed architecture. All right. We will talk about all the tools and we will make sure that our definition is intact as we go ahead with various definitions of various products. All right. Now we confuse distributed computing with parallel computing. In parallel computing, you have multiple processors sharing the same memory. Okay, we do not utilize the network in case of parallel computing, but good part is good part is any system which is distributed can be paralleled, because if we are able to divide our processing into multiple computers, we can also divide our processing to multiple processors. But the other way around is not true. Every system which can be every code or every product or every requirement which is working on parallel not necessarily can immediately move to distributed. All right. So, so in parallel, you have multiple processors but single memory. In case of a distributed, the computers communicate. Each computer has got a memory and a processor. They communicate over the network. So each individual unit is a full CPU, full computer containing everything. All right. So keep that in mind. So we have the definition of distributed computing is we have multitude of computers. They all work towards a single goal, or a single goal is given to all of these nodes simultaneously, and they work together. All right. Now there is always a question of what is structured, because in our definition, when we said structured and unstructured, let me define the structured and unstructured. So a data is structured if we know clearly what are the fields in the input, as well as what are the data type of each field, such as the data in our database. All right. Semi structured, where we know what are the fields in the input, but we do not know what are the data types of each field, such as comma separated file. Unstructured, we do not know what are the fields in the input. We'll have to parse it to segregate the fields, and we do not know what are their data types, of course. When we do not know the fields, how can we know the data types of each field, right? So therefore, such data is called unstructured data. Ravidas's question is, does that mean parallel has only one machine, one server, since it has single memory, and distributed has one or more servers? Generally, it is that way. When we say parallel computing, it's a single machine containing multiple processors working on the same memory. Good question. Yeah. All right. Now, I'm extending our definition. So we'll stick to this definition as we go ahead, because there seems to be a lot of hubbub about the definition of big data. The big data is all about distributed computing. All right. Nitika's point is it's like multi-processing. Yeah, sort of having a multi-processor system is sort of a parallel computing environment. All right. Now, what exactly is big data in a traditional definition given by IBM and others? The definition is we characterize big data by four V's. And first V is volume. If the data has got huge volume that one machine cannot handle, we call it big data. In case we have got so high velocity that one machine cannot handle, meaning lot of requests coming from the users, then again the same definition. And third is variety. If the data has lot of types, or the kind of processing which we a little bit extension of variety, the kind of processing we are doing on our data, if it is complex, then also even the small data with a small volume and small velocity can become a big data problem. All right, I'll give you one example of each. Fourth one is veracity. Veracity is when, due to confusion or incompleteness of our investigation on data, if we lead, we might uh, end up with lot of data, lot of volume or velocity, and hence it could be a big data problem. Let's take one case of all. So when you use Facebook and you upload data, at the end of day Facebook accumulates a lot of files, lot of data from all the users. That is volume. But at every point of time, and to handle such a volume, Facebook would require thousands of servers to store it. Similarly, we have got velocity. At the same time, lot of people are accessing their accounts, seeing the update, and at the same time all of them are requesting Facebook for their status, for their news feed, right? That that is causing a lot of velocity on Facebook, velocity of request on the Facebook servers. All right. Third is variety. When you have a complex, so many users connected in so many ways, having so many common friends, and you try to analyze this. Okay. So the structure of the data when we talk about the complexity is high, right? It is a graph and it needs to be processed using different set of algorithms, and that is what is known as variety. Okay. Or the data could be in the form of map. So another example of variety would be, take a case of Google Maps. Google Maps of the entire country will be hardly few GB, or maybe say 50 GB, all right, for the entire country. Now, let me just turn off my phone. All right. So for the entire country, the Google Maps could be as small as 20 GB, right? It's not a big volume, neither there is velocity, but the problem of finding a path from one point to another in a graph is a complex problem, and hence the data is considered complex. And the whole, and that's what is known as the variety of data or variety of problem that might make your data big data. All right. Fourth is veracity. Imagine that for for the whole world, if we have, just a second, lot of sound is coming. Yeah. So the example I would like to quote for veracity is, imagine that we have got data from 10 sources. The data is temperature data of whole world. Okay, we have got this temperature data from 10 different sources in 10 different formats. One format gives us data zip code wise, while other format gives us data from GPS coordinates, and another one gives us the GPS coordinate wise data but broken down into seconds level, and so on. There could be multiple sources of the data. Now it will take some time for you to realize that only one of the data is most useful for you, and therefore you need, but you have to find out which data out of these 10 data sets. But till then, till you realize, till the point you realize uh, that this data set is important to you, out of these 10 data sets, you will have to store and churn all of these 10 data sets, right? Because that is how you will investigate and figure out which data set is important to you. And therefore this confusion caused the higher volume and might take you to the big data side. Now Sanjay's question is, why is there a star next to the veracity? Okay, so yeah, that was out of the diagram, and veracity, the asterisk actually said that this was The veracity was introduced into definition in 2014. Right. Paras's question is how to set phone call. So actually, if you make a phone call, it will be a IST international call for you. All right, and I'll have to interrupt the session. Okay. So, all right. So, is the example of veracity clear? No. Let me again describe what I just told. So, if you get data sets from 10 different sources, or you already have data sets from 10 different sources, now to churn all of these 10 data sets, you will have to have some kind of a big data processing system. And till the point you realize that only one data set is important to you, or all of them are important to you. Okay. So, yes, thank you, Sanjay. Even in healthcare industry, you will realize that same data is available from different vendors, different formats, and you just have to churn all these data sets in order to realize that the in order to zero down on one of the data sets. So the veracity, meaning the confusion, uncertainty, and and maybe a state in which you need to take a decision amongst various data sets. Make sense, Nitika? Chidamran? Ravidas's point is, but veracity depends on person to person since it is not deterministic. So in such case, how come it will be accurately analyzed? Yeah, that's a very good point, Ravidas. The thing is, it's not person to person. It's problem statement to problem statement. So imagine that the temperature example which I gave you, imagine that you don't need that fine grained data. Okay, you only need hourly data, and that too on the zip code wise, right? So if you are so your requirement is such that, then you can clear up the confusion immediately. Now in case you realize that this zip code data might have errors in it, and you need to check its sanctity by comparing it against other data sets, right? Then it will become a little bit more difficult and a big data problem. All right. Data quality is another term for veracity. Thank you, Sanjay. And it's the same thing. Yeah. Great, great. Happy to answer your questions. Now, a quick check if you are with me or not. So, how many bytes are there in petabytes? Quickly, the first answer, and I'll move. Yes. How many bytes are there in a petabyte? 1024 GB. That is 1 terabyte. Because yes, 1024 TB is correct one. Good, good. 10 to the power 15. Thank you, Trilok. Thank you, Vikas. And Tarak, thank you. 10 to the power 15 bytes. Excellent. So all of you know now. Great. Good, Pop. And yeah. So we have got 10 to the power 15 bytes, close to 10 to the power 15 bytes. And the better way is to remember this way. And although these numbers are just two syllable words, you will realize that they are really, really difficult to solve. So a byte is 8 bits, and 8 bits which can store 256 states. So it can store 256 states. All right. So basically 10 to the 15 is a huge data. States as in, if you think about your bulb switch, the switch that turns on the light, it is one bit of information. Either it would be on or it would be off. So a light bulb actually stores one bit of information, and that is whether it's on or off. Not bulb, but switch. So if you have, you know, 20 switches, you can store numbers up to, you know, you can store a lot of information in the switches. Herschel's question is is there any limit of big data to process data? Not really, not really. As long as you can keep on adding the machines in the network and the network can handle it, there's not much of a limit. Although, although some of the systems which have been designed for big data might fail beyond yottabytes or beyond maybe exabytes, but the definition actually says that you should be able to handle any size of data using a lot of computers. So big data tools would have their limitations. Now we know how much is petabyte. We know what is big data. So my question to all of you is 1 petabyte big data? And what do we mean by 1 petabyte data here? We are just trying to store and retrieve 1 petabyte data in a reasonable amount of time. We are trying to just store, or let's say I give you a very simple example. You have got 1 petabyte numbers, and every day you just have to find average of all those numbers. Okay, you have to find mean of those numbers every day. That's a kind of job you want to do every day. At the end of day, you want to just go through all the numbers and find average. Now my question to you is 1 petabyte big data or small data? All right, Paras's question is, I want to computer audio. Do you want to speak or you want to unmute? Sweta is saying, is there a minimum data requirement for which we should go for big data? That is correct, Sweta. So any data, if you can handle happily using a single computer, you do not need any of the big data tools. All right. If you see in the near future that your data is not going to grow bigger than what can be handled by a single computer, then there is no need to move to big data. And we will discuss it in detail. It's a very good question. We'll discuss in detail why, because if you can handle something using one computer, you should not move that to Hadoop or any other system. All right. So Nitika says yes, it's a big data. Tarak says yes, it's a big data. And Renia says yes, it's a big data. Vikas also yes. And Tarak says that it's computation of 1 petabyte data is big data. Sanjay also says yes. And his answer is because 1 petabyte cannot be stored in one computer. That's good. Yeah. Sweta says yes, it's a big data. Okay. So everybody is conquering at the point that this is a big data. Yes. Good, Vikas. Okay, there are two Vikas, one Vikas Mishra and Goyal. All right, Mishra. So I'll call you just Mishra, so that's it here. If we have good, good. Yes, thank you, Vikas Goel. If we try to churn 1 petabyte data with usual tool, it will take much too much time. That is correct, and it depends on data. If data grows, yes. All right, great, excellent. So all of you agree that 1 petabyte is a big data. All right. So I talked to many few telcos, few people. The moment their data goes beyond few terabytes, existing disks, existing file system starts to falter. And the biggest reason is the rate at which you read the data from disk becomes really, really slow. Okay. Let me just create a quick question for you. Okay. Now my next question to you is, how much time does it take to read 1 TB? Anyone? How much time do you think it takes to read 1 terabyte data? Sweta says 6 hours. Anybody else? It's a single processor system. It does not depend, it actually does not depend on number of processors. I think I should add that as another question. Yes, that's correct, Piyush. It does not depend number of processors you have. What it depends upon is how fast is your disk and how big is your data bus. Yes, that's correct, Huda. It depends upon the hardware, right? Hardware as in, um, how big, how good is your disk? Because when you are reading the data from a disk, CPU is hardly utilized. Okay, CPU is free. So I've got best answer so far from Sweta, that is 6 hours. Good. And Vikas says more than 1 hour on your user machine. If RAM is 8 GB, then 2 hours. How does it relate to RAM, Vinay? I would like to understand that. Ravida says more than 5 hours. Good. And Huda says computer processor. But you know, as opposed to the common sense, the computer processor does not play any role in in case of a reading from disk. It totally depends on this. Good. All right. So yes. So it takes close to around, on the fastest machine, it takes around 6 hours. Okay. But for me, it takes around 24 hours. My disks are fairly slow. So okay. On my usual disk, which I use at home, the copying of 1 terabyte takes close to 14 hours. Maybe it's a bottleneck of the network, but that's what I've measured. All right. So my question here is, what I wanted to show you, or explain to you, that when we talk about big data, as in the previous problem, okay, in the previous problem when we talked about storing 1 terabyte, 1 petabyte of data, the the bottleneck will be on the file system side. If we have to read 1 petabyte data, it is going to anyway take around 6,000 hours. All right, to read 1 petabyte data from a single disk is going to take 6,000 hours. So, in no way, if you have to process 1 petabyte data from a single computer, it is going to take 6,000 hours. Even if you are just counting words. If you're just counting words, let's say your objective is find out how many times alphabet A has been repeated in this 1 petabyte data. All right, so that too will take minimum of 6,000 hours on a single computer. That is why that is why it is impractical to handle 1 petabyte of data using a single machine in any way. So it's a hypothetical question because there is no disk of 1 petabyte size and there is no machine which can handle so many disks in a single motherboard. So what size is required for it? That is Nitika's question. Could you reframe it? I think I lost the context. All right. So till that point of time, I'll describe the big data. So why are we talking about such a big data now? The simple reason is in 2002, the digital storage started increasing exponentially. All right. In 2002, the digital age started, and why did it happen that way? So you can see easily by 2007 the digital data is around 280 while analog is shrinking, analog as in paper and film and analog videotapes etc. The digital data has started expanding exponentially. This looks this looks like a linear graph, but it's actually like exponential. Okay, so now why did it happen that way? The simple answer is devices and the network. While devices produced a lot of data, network multiplies that. For example, I'm talking right now, I'm sending around 1 gigabyte of data, and since there are around 50 people, 40 people in this session, there are around 40 people in this session. That means by the end of the session, I would have transmitted 40 gigabytes of data. All right. So while devices create the data, network multiplies it. And that's the reason these two things, on one hand, devices kept on becoming cheaper, faster, and smaller. These are the three keywords which every hardware manufacturer in electronics industry follows: cheaper, faster, and smaller. Every hardware manufacturer kept on pushing the boundaries of cheaper, faster, and smaller. And today we have every one of us have a phone in our pocket which is far more powerful than supercomputer of 2000. Right, in year 2000 we our supercomputer was around 1 gigahertz. Now our phone is dual core with more than 2 gigahertz. So devices became cheaper, faster, and smaller on one hand. On the other hand, the network became more and more available, meaning people got connected more and more, hardware wise as well as software wise. And on hardware wise, the devices also got connected a lot. And that's what caused the data to be exploded so much, right? Now, you might say that we can simply ignore this data, right? Why do we need it? The answer is, let me, okay. So I'll talk about this a little bit more later under the uses of big data. So the simple answer is, when you have access to a lot of big data, you can do a lot of magic. All right, we will show you that part. Why does it need magic? Nitika's question is, if it takes 6 hours to read 1 terabyte, what size is required for 1 petabyte data? Right? That is why whenever you have to deal with petabytes of data, what you do is you have maybe 5 6,000 of computers working parallelly, and each one of them holding only a section of data. So size of hard disk is not has not gone beyond a few terabytes. All right. Yeah. So the graph was here. I was talking about this graph, Vivek. I'm sorry to uh, move next. All right. So we talked about the pace at which data has grown, and the reason why the data has grown so big. Now let's talk about a little bit more about why is it such a big deal to handle such a data. All right. Now my question to you is, what components affect the speed of computing? Yeah. Vinay's question is, as of now, because of virtualization, the companies like Facebook can process petabytes of data. Not virtualization, most like distributed computing, Vinay. So Vinay's question is, as of now, because of virtualization, the IT companies like Facebook can process petabyte of data faster. So yes, virtualizations coupled with distribution and distributed computing is what makes big data companies solve the problem of very humongous data. Nitika says memory. Vivek says all. Goyal also, Vikas Goyal says all. Shweta says C. Okay. Disk size is Nitika. Okay. So finally, Vinay says, okay. All right. Sanjay says all of above. Tarak says all of above. Pop says all of above. And Vikas says all. Renia also. All right. So Ravidas says CPU, memory disk, and speed. Okay. Okay. Vinay says, all right. So the thing is, all of them, all of the above, that is G, the all of these components A to F impact the speed of computing. All right. Yes, that's correct, Ruda. Great, great. Now, so whenever we deal with any problem, okay, these are the four components which impact the most. First is CPU. CPU is something which reads the data from memory, processes it, puts it into memory or disk or over the network. So CPU is the main player, the active player, which reads data from here and there, processes it, and runs the logic. Processes means running your logic, as in following some instructions, and then do the magic. Yeah, it's a brain of the computer, you can say, but these are also all part of the brain. So if the memory is down, memory is smaller, CPU will be uh, slower, slower, right? Now, you will be surprised, all of you will be surprised that most of the servers have their CPU fairly free. Even your computer, if you notice your computer and plot a graph of the CPU utilization, your CPU is going to be hardly utilized 1% of the time if you average over the whole of the hours. Okay, so CPU is generally not bottleneck. It is only the companies like Intel and AMD uh, who has been feeding us that buy a faster CPU, but CPU is hardly of a problem. All right. There are other components which impact the computing, such as memory. If your RAM is smaller, no matter what you do, your system is going to be very, very slow. Fourth is the network, or let's talk about third, which is disk speed. If you buy, and the interesting part is, if you just replace your hard disk, normal computer's hard disk, with a solid state drive, you will suddenly notice a humongous performance increase. All right. So, for example, our website runs on solid state drive, and our website has a very small specs, and it handles lot of users parallelly. And only at a later point of time we realize that it is the disk speed which mattered a lot when dealing with e- even the website. Okay. Fourth is the network. When your data starts growing bigger or the velocity of the users is too high, it's the network speed which matters a lot. So we cannot ignore any of these components at any point of time. And when it comes to big data, at least one of these components becomes such a humongous bottleneck that you cannot handle it using single computer, and there is no other way than moving your computing to multiple computers simultaneously. All right. So basically, out of these four things, at least one will become such a bottleneck, then you will have to move to to multiple computers. All right. If RAM, and mostly it's the RAM which becomes the first bottleneck. If you you go through the case study of Wikipedia, it was the RAM which became the bottleneck first, then the CPU. All right. Yeah. So Sanjay, I hope I answered your question. Between RAM, disk size, and disk speed, network, which one has most impact on computing speed? Probably it is the RAM, because the CPU is fairly fast. Even 1 gigahertz processor is actually fairly fast. If your CPU is going really, really busy, if your CPU is really going to be very, very busy, like 100% utilization, probably you have left a infinite loop in your code. There is somewhere there is a bad logic. All right. If your CPU is really spinning at 100%, therefore CPU is hardly much of a problem as compared to RAM. But in the cases like image recognition, sometimes CPU does become a bottleneck. All right. And when the CPU becomes a bottleneck, it becomes really, really big problem. Okay. So you might have to figure out a better algorithm than replacing a CPU when CPU becomes a bottleneck. All right. All right. So now my your question would be, then, when we had such a big data and it's such a problem, our these all components are falling apart. Why? What is the point exactly in handling such a big data? Why don't we just delete the data instead of accumulating or trying to process it, right? Now, the reason is, there are there are a bunch of useful things about big data. First, the law of large numbers. Okay, law of large numbers says that if you flip a coin enough times, then after a while, if you do, it will be the ratio between head and tails will be 1 is to 1. Okay, so if you flip a coin enough number of times, then the ratio will be 1 is to 1. But if you just flip it 2 or 3 times, The ratio is not going to be same. Now let's replace the coin with the dice with 1,000 faces, right? So a dice with 1,000 faces has to be flipped at least 1 million times to get really uniform distribution of the outcome, right? Similarly, Similarly, if you have to compute average, let's say we are saying what is the average number of people in this world who will be interested in big data? Okay, and if we just go ahead and gather the data from Bangalore and try to analyze it, or do a small sample from all across the geographies, and after that churning of data we start saying that it's only these many people who are interested, there are high chances that your analysis is wrong because it's based on a very small data. All right. All right. So let me again take a step back. Nitika's question is, can you repeat it? Let me take a step back and ask you a simple question. I think I would have another one. I will talk about it a bit more. All right. I'll actually, yeah. My question to you, all of you, is there are two hospitals, okay? A and B. Both are honest, okay? A reports that the girl the total girl children that took birth are 60%, and B says B says it's 49%. So which one, A or B, more has handled more births? So there are two hospitals, A and B. Both are honest. A reports that total girl children that took birth are 60% of total births. And B says it's 49. Out of 100 children that took birth, 49 were girl children. So which one do you think has more number of births? A or B? Which one has more number of patients, I mean, more number of cases? Sanjay says B because that is closer to 50%, so more volume. B. So yeah, cool. That because thank you Trilok, thank you Sanjay, and thank you Vikas, and Mishra. Uh, Okay. So the thing is, the one having higher volume, their prediction will be higher. If if a hospital just got 20 births and out of that mostly were girls, it might be a very biased set. The data is insufficient to take a decision, right? Therefore, the bigger the volume, the better will be predictions. Okay? The more the volume you have, the better will be predictions. That is correct, Vinay. Thank you, Vikas. All of you are correct. Yes. And Piyush says cannot say. Piyush and Vivek say that cannot say. Okay. So the thing is that the the hospital with bigger data will have more closer predictions to the actual one. All right. So here we are assuming that the the girl and boy births are equivalent. Rania is saying that can we ask another question? It will be better. Yeah. So other question was that in case there are two guys, okay? In case there are two persons given the same dice to throw, okay? Throw a million times, throw enough number of times and report percentage times 6 appeared and person reports that it is a total of 1 by 6th. Alright, it is 1 by 6th of total times, while second one second one says otherwise. So which one out of first or second, okay, who has rolled dice more number of times? You got the answer? Alright, so that's a law of large numbers. We call it law of large numbers. Alright, going ahead on the same lines as, yeah, that is correct. The second one, no, the first one is more closer to reality. Huh? Alright, because the first person is the correct because total number of times 6 will appear is 1/6 of the total, and therefore uh, and therefore the one who rolls the dice enough number of times will get those numbers. All right, now going ahead on the similar line is something called recommendation engine. Okay, recommendation engine is something which takes your data and gives you recommendation. For example, in this diagram, it's a recommendation from Amazon. It shows that people who bought this also bought these dresses, or you can wear this dress with these other things, right? This is based on a historical data. Okay, so so if you have sufficient amount of data, you can do really, really wonderful recommendations. In case you have small data, you cannot really do any useful prediction. Okay, so that's where the big data solves a lot of problem, and you will be surprised that after emails Amazon makes most of its sales through recommendations. I come from an Amazon kind of background, so I understand that giving recommendation is something really, really important. The difference between spamming somebody and showing something useful is big data. If I keep on selling you some things like these are the latest things in our market, buy these, buy these, buy these, you will get irritated by my recommendations. If I tell you that, hey, based on your past history, I think you are going to like these, you will say, hey, thank you for these recommendations, because if my recommendations are really useful to you, right? And I can give you those kind of recommendations only if I have sufficient amount of data about your past behavior, right? So what Amazon does is Amazon keeps on recording all the products you visited on the website, all the products you added into cart, all the products that you have rated higher, all the products that you have purchased for yourself or somebody else. And based on all of these parameters, it starts giving you the recommendations that people like you generally buy this, or people who bought this. In case I have no history about you, I will tell you that, hey, all those people who looked at this particular shirt also looked at this. People who bought this also bought this. That means I am able to do a counter sell. And when you deal with it, the bigger data is better. And that's why Amazon keeps track of the history of all the users for years. And same way, when I built my first recommendation engine, we churned a lot of data to analyze people's behavior. Even our 3 months data was close to 200 terabytes. Okay, at InMobi, where we were giving you instead of showing you an ad, I was showing you that uh, that since you have been playing these games, you might also like to play this game. Okay, and that actually increased lot of lot of conversions to our website. All right, so last point, sorry Nitika, I missed the question. So last point, which one? Tarak's question is also a basic recommendation, say number of times the same item is viewed, and based on that the product is recommended. That is correct, Tarak. So all of this computation, the interesting part is, as a big data engineer or analytics, your role will be to convert the behavior of the user into his preference towards a product. And I'll show you how. All right. Pusey's question is, do big data technologies help analyze predictive analytics, the data also? Of course, this whole is predictive. The reason is these predictive analytics tool has been around for quite a while, even before the big data innovations. The only problem with those tools was and is that they did not deal with data in 100 terabytes. They dealt with the data which can be handled on a single computer. So, for example, if you take R is a programming language. The algorithm it represents for giving recommendations cannot be used to tackle big data so easily. Reason being, all its algorithms are designed to run on only a single computer. While for recommendation of big data, you would like to go for something like Mahout, which can run your recommendation engine on multiple multitude of computers simultaneously. I'll show you that. All right. So Nitika's point is, second question you have asked, the dice problem. Okay, we can discuss it offline. Is that okay? I'll reply to you. Okay. I'll just take a note. Okay. Okay. Ravidas says that, is this related to consumer insights? So Piyush says that means R cannot be used on big data. Generally not. R is good when the data is good enough to be handled on single computer. But when your data does not fit into a single computer's RAM, R is not a solution. Although people are working on something called distributed R, but still that's in a very premature state. Make sense, Nitika, now? All right. Yeah, that's what I was answering. So let me answer again why we cannot use R for big data handling. Problem with R is R handles everything on a single computer. There are other solutions like distributed R, but they are in a very premature state. So if your data does not fit into computer's memory, then you cannot use R unless of course you go and buy 100 GB RAM. Okay? But that too is not much of a solution. Your data generally goes beyond 100 GB. Trust me, if you are even a small company like no big data and the data you are churning over a year of time when you are recording computer your users behavior, it goes beyond terabytes. All right. So good. So these are few examples. The other examples of recommendation engine is the IMDb or Netflix. And that's where the whole thing started with big data. So Netflix ran a competition where they declared a $1 million prize for the person who creates the best recommendation. Similarly, on IMDb, when you go there, you based on your history, it gives you the recommendations. Okay, it gives you the recommendations clearly. So how do most of these tools work is they take the data, they try to correlate who all are the users similar to you, what all products look similar to each other, and they cluster the products, they cluster the users and give you the recommendation. The general format is the simple one where we are not talking about the product's detail. The most simple recommendation is of this format. We have user ID, we have movie ID or product ID, we call it product ID, user ID, and then rating. So whether this product is a movie or it's a cloth, it's up to you how you structure your problem. But engines like Mahout will take the data in three column format: user ID, product ID, and the rating. The rating has to be something between 0 to 5, 5 inclusive, and will give you the recommendations. Okay, so since the tools like Mahat or other libraries, they just take the data, give you the output. Now you might ask, then when Mahat does everything for you, what is your role? Your role is to prepare the data in this format: user ID, movie, product ID, and the rating. And trust me, it takes a lot of engineering to deal with big data and prepare this data. I have seen it in past, and I saw even the most of the data scientists failing to get it done. Reason being, we still think in terms of the older way of doing things. All right. So this is how you do a basic recommendation. You convert your problem statement, you convert your whole complex data into this three format. The user I in three columns. First column is user ID, second column is a product ID, third column is how much this user likes this product. And you feed it to Mahat and voila, it'll give you user ID, product ID, and how much this user is going to like this product. Okay, how much this user is going to like this particular movie, and and that's a magic part done by these tools. So this is how you generally do the recommendation. Okay, we will go in our sessions into the details and we will build one movie recommender as we go ahead in the probably session number 6. But before that we'll do this problem in parts: importing data, converting data, translating it to something, and so on. All right, now going back, Going back, now the other use case of big data is sentiment analysis. Although the sentiment analysis has been around for more than 10 years, even in this area, but every day it improves. Every day there are newer techniques to do the sentiment analysis. The first and most simple one is a simple statistics one, where we and let me first describe what does it mean by sentiment analysis. So you are a political leader who wants to see how did your last speech impact, right? So you made some statement in the public about few things, and then you basically hooked to Twitter, went through each tweet and understood whether people talked about you negative or positive, and then you accumulated all of it, and then you plotted a graph over a period of time saying people talked about me very nicely on the first day, then very bad, then there were so many negative comments, there were so many positive, and so on. You plot this graph, and then you put the events in place saying, okay, I made a public speech on November 26th evening. So on November by November 27, November 26th evening, there is a huge positive impact, but then it went down. And on here, let's say this point on November 28th at around 2 p.m., I made some statement because of which I suddenly went down with popularity, right? So you prepare this kind of a presentation and then try to figure out what is working and what is not working with respect to your campaigns. And you may be a political leader, or you might be a somebody who is managing a brand of McDonald's, KFC, or your own organization. You want to see how how is the sentiment towards you from the public. The sentiment analysis can be done from public sources like Twitter or other forms such as Facebook comments, such as Facebook likes, and and maybe on other forums. Okay, maybe on another forums. So that is how that this is what is known as sentiment analysis. We will deal with sentiment analysis problem in one of the sessions. Okay, the other use cases of big data is improving the search quality. Even if your data is small, you are building a local search engine for your local intranet. Even then, you might have to occasionally churn big data to form various kinds of dictionaries, various kinds of weightages, in order to provide your users really brilliant suggestions. Say, when people type a wrong thing, you can give an alternative, or maybe you can provide them with the image search. So when I was working with Tbits Global, my own company, where we were working on the problems of searching in the data in the documents, that time I realized that unless and until I form a global dictionary of a global thesaurus of various words, my customers are not going to be happy with my search engine. That is when I improved upon the search quality by crawling a lot of data, by either buying the dictionaries or forming the dictionaries. Okay, if you try to form the dictionaries by crawling the data, then you inevitably require a big data solution. All right, so I think it's a time for taking a break. How do we get a data feed from social website? So there are multiple ways. Most of that is Sweta's question. There are multiple ways. First one is all of these systems provide you the API. Go through those APIs, or you can write the scrapers. There are tools using wget, or there are multiple tools, multiple um, libraries in every programming language that let you download the data from various websites, and also they let you process the data. Okay. So before we take a break, we have a query from Mishra. Just one query. Will we get a chance to do hands-on on these things like sentiment analysis recommended? Of course, of course. Those are, so his question is, will you get, as a student, will we get the get to do recommendation engine or sentiment analysis? The answer is yes, you will have to do that as exercise of our sessions. Okay, and I'll make sure that you do that. All right. So yes, you will have to do a practical implementation of it. Okay, I'll guide you through the whole course, and we'll do it in parts. Okay, from the day zero, from the second session onwards, we will be doing solving our problem in parts. All right, and in the session 6 we'll do the recommendation, and in the last session we'll do the sentiment analysis. Till then we'll do it in parts. Okay, so yeah, now I think we should take a quick break. Let's come back at 10:13 p.m., which is around 10 minutes from now. All right, let's take a break for 10 minutes. Hi, I'm back. Should we start now? Yes? Great. Great. So should we start everybody? I've got yes with okay. Almost everybody's ready. All right. So everybody able to hear me? Awesome. Now, so other than recommendation engines, we can utilize big data and people are actually utilizing big data in terms of improving search quality, sentiment analysis as we talked earlier, and ad targeting. In ad targeting, that is very specific problem to few companies, but in ad targeting what companies do is based on one hand there are many people who want to show the advertisements, and on the other side there are various advertising slots available. Advertising slots could be on the websites, could be on the mobile applications, could be within the game, and so on. So to find out to do the best matching, that the ad which is most relevant to the right users should be shown correctly, and that ad targeting is a humongous problem. All right. A/B testing. Does anybody know about A/B testing? All right. So only Vikas knows and Nitika knows. Good. All right. So it's not really like a beta testing. A/B testing is, let me just open another text editor. Yeah. So what does it mean by A/B testing? So organizations like Amazon, they keep on making changes every day. Okay. Every day, every feature is being changed. And the way they do it, the they whenever I'm pushing a particular change, say I came up with the idea that buy now button should be blue instead of green. So I will change the color and will say that, okay, please run my buy now button or show my buy now button only to 1% users, and for 99% let the existing be as is. Okay, so one set, the existing one is called A. Let the A set be as is for 99% of the users, and let this 1% users, which is B, they keep let them see my new button. All right. So instead of taking a risk that we just replace this old button with a new button, what I have done is I have only taken a small sample of the users, and that I have given it to my I have shown this button to only few users out of the total set. That way I will be able to measure the performance of my button, and only if people are clicking more on my button, the new one, the new change which I have made, only then I'll keep on increasing the number of users who see my button. And at the end of day, after a point of time when I have proven that my button gets more click than the older one, that means we can totally give the whole traffic to the new one. Okay. So whenever you are building a feature in your website, instead of just removing the feature and adding a new one, you should always have A/B testing framework in place. Okay. An A/B testing framework will make sure that you can make changes to parts of the website and still uh, and these new changes you serve only to few users, not all. So that is called A/B testing. Yeah, great to know, Vikas, that you do it on IndiaMart, and only few companies do it in that way, right? Now, Tarak's question is it similar to WhatsApp calling feature? Yes, you are right. So the way WhatsApp only shipped their calling feature to only few people, in the same way, whenever you are rolling out a change, you only roll out to few people and then compare the performance against the older version. So now you have two things running in production. One is older, other is newer, and you're comparing these two, and that is A and B. We are testing A and B against each other. All right. So that's what is A/B testing. And A/B testing as a phenomena requires a lot of big data handling in terms of velocity. All right. If your website has got a humongous number of requests coming in from the user, you would require a solid A/B testing system which can handle a really high velocity of the request coming in. Make sense to you? The other users which are really high is telecom. So, for example, yesterday or day before, one of the users from one of my ex-students called up. Their company was basically facing a challenge in handling the configuration of various instruments. So, what they generally do is there are a lot of instruments and they keep on changing the configuration. Even a simple thing as configuration management takes a lot of time for them. Each instrument's configuration over a period of time goes into terabytes. All right. And using existing system, even the loading is taking so much time that it is becoming very impossible for them. So telecom companies are by default the users of big data. They have many uses, be it be it as complex as customer churn prevention, figuring out why people are leaving them. If they have the record of how many times a user called the helpline, how many times user wrote the email to them, how much time user was out of coverage area, if they do a correlation between this data, they will be easily able to figure out why did the customer leave them. Okay, and in case they can figure out why customer leave them, they can avoid customer leaving them by providing them a better service, a better service in terms of a support, in terms of a quality of the network, and so on. They can do a lot of network they do a lot of network performance optimization using big data. Basically, they figure out the pattern of data usage over the whole city in order to optimize the resources. They figure out that on working day, people work more from electronic city uh, or high tech city instead of homes, and therefore they have to increase the capacity in these regions on a typical working day. So those are the kind of network performance optimization they can figure out. They, and they are figuring out using big data tools and technologies. They can do a caller data analysis, and they can also do a prediction of prediction of failure. Okay, so if we know that the way we prepare recommendation, this user, this product, this much is the recommendation. So what will be similar in the similar fashion, people can also do a prediction of failure. These circumstances and it failed. These circumstances and it failed. And you feed it to one of the algorithm and it will give you the result that in these circumstances it will fail or not. Okay, so those kind of these are the few few big data customers. All right. So yeah, these are few big data customers, and there are many more, such as government, maybe in fraud detection, in cybersecurity welfare, in justice, in healthcare and life sciences. It is very obvious that because in healthcare, almost every data is big by nature. Okay, as simple as the X-ray records, by definition, are very complex data. So, in healthcare, you have volume, velocity, and variety by default. And and the kind of problem healthcare solve is related to life. So, it is important that a lot of companies should work on healthcare, and they are working and utilizing big data in terms of health information exchange, gene sequencing, healthcare improvements, and drug safety. Okay. Recently, Google also did a lot of research. They started predicting the disease based on various kinds of criterias. Okay. There was a recent paper. So whenever there is a humongous data involved, you would require big data tools inevitably. These are just few examples of where people are using big data. There are billions of cases right now. There are millions of solutions, various kinds of problems people are trying to solve using these tools and techniques. Make sense to you? And there are many more. This diagram I prepared out of Hadoop. This font size of each of these companies equivalent to number of Hadoop instances they had, and so on. Okay, because it's not that big data means Hadoop, it's just that the data was easily available for us. Okay, here are few of the common myths. Stop me if you think it's really not a myth. So if you have a doubt about any of these 11 myths, stop me. I'll just go through one by one. So big data always means data above or in the range of terabyte, right? That we have discussed. Yeah, John, you have raised a hand. You have a question? I'm sorry, I just saw the hand just now. We have a question from Vikas Goel. If we are storing data with Cassandra, then will we be able to use it as big data? Of course, Cassandra is a big data solution, right? Cassandra is a solution which runs on multitude of computers parallelly and solves a lot of churning problems. Yeah, good question. Now, anybody else? All right. Yeah. So there are 11 myths. First one is obvious. Of course, there could be, as I was talking about Google Maps example, the pathfinding problem or finding, categorizing information, even if data is in gigabytes, the problem is complex. The data by nature is complex. Okay. Second is it's always social media. No, it's not always about social media. There are a lot of problems which could be solved, are being solved using big data. It will replace EDW, which is Enterprise Data Warehouse. It will not replace EDW because EDW is really brilliant when it comes to handling gigabytes of data, not terabytes, gigabytes of data in a structural manner, in a relational manner, having some sort of transactions, good enough transactions. So EDW is brilliant when it comes to managing transactional data. Okay. So none of the big data solutions can replace EDW so easily. We will go into those details. Why can't big data solution be used in transactional environments? Okay. fairly difficult. None of the big data solutions tries to guarantee the transaction. All right. Now, which okay, so I think I asked some question I did not see. Now, Sweta's point is that what is Cassandra? Is it related to Hadoop? So, Cassandra, in very simple words, is a database which runs on multiple computers simultaneously, storing the records on multiple computers simultaneously, maybe thousands of computers, so that it can handle gigabytes of data, billions of rows, and do computing using multitude of computers. All right, that is Cassandra. So Cassandra is one of the big data solutions. All right. Next is big data is just a buzz, no practical applications. So of course, it's not a buzzword. It's a new concept. It's not new concept. As I was telling you that even in case of our D short time, we did solve big data problem in the similar manner, not in the same manner, but in the similar manner. And we used to call it grid computing. All right. It's not a new concept, it's an old concept. It's just the name is different. It will be the future. No, it is the present. Okay. Is expensive? No. Almost all big data solutions are designed to be very cost effective. Okay. In licensing terms, all the big data solutions, almost all of them are open source. The documentation is available. There are a lot of people who have access to the information as opposed to the closed source one, because of which the technology as well as the tools used to be very costly. Now, is only for data scientists or is magic? No, data scientists do make some algorithm. Like in case of Mahad, the actual algorithm would be written by some data scientist, but but 99% of the work goes into churning and cleaning up and executing and figuring out which algorithm to use. Okay, so it's no longer a magic. We have enough hardware, we don't need it anymore. So it's not about hardware, it's about the architecture. Lots of solutions, all of them run almost on any hardware, and the design is such that you can utilize any typical hardware into the any commonly available hardware to for any of these tools. Okay, you don't have to buy special hardware. We will buy it when we need it. We will build it when we need it. This is another myth that goes around. Most of the complacent people who are, you know, busy with their normal things, the common excuse they give it that we don't think we need these kind of things right now, and therefore we will not think about it. The problem is the moment they realize that, oh, they need big data solutions to do so much about their customers, that point of time they had already lost so much of data, because they had no place to store so much of data, and hence all of the developers, everybody was having hesitation in storing so many customer errors people are facing, and logs, what is it, which website people are visiting. So all of that data they must have already lost, because the they did not build a good brilliant solution to store data. So this is another myth. So ideally people should just build at least a solution where they can store. Churning they can do it later. And big data is about Hadoop. So no, big data is not about Hadoop. It just so happens that Hadoop seems to be most complete solution when it comes to distributed computing. There are many others. I'll show you few of them after this slide. All right. So yeah, I will. Okay, let me take up your questions. Sweta's question is it real time? Meaning, is Cassandra real time? Not much, but yeah, close to real time, but not really. Subramaniam says, what is MapR? MapR is a company which provides the Hadoop installations, Hadoop packages, and provides support on MapR. Cloudera, Hortonworks, and MapR. Though MapR also signifies map and reduce, which is a programming or computing paradigm, just like for loop or just like publisher subscriber. Similarly, those there is a paradigm called map and reduce, by which we can distribute our logic of computing. Now Vivek's question is, what is difference between grid computing and big data architectures? Is it just the absence of centralized frameworks like Hadoop? So Vivek's question, let me answer Vivek. So his question is there a difference between grid computing and big data architectures? So big data solutions and grid computing is not much of a difference. In grid computing, we used to distribute our logic across the grid and get it executed, while in similar thing we do in big data architectures also. Say the way Apache Spark works, they call the whole thing as grid computing, if you notice. So so there is not much of a difference between big data architectures and grid computing, just that there are few more paradigms that have been introduced, such as map and reduce. That is a paradigm that has been introduced that was not there in grid computing, but we had different forms of. Yes, John, you have a question for me? You can type the question. All right. So these are common myths, and we are talking about common myths. So I hope I've answered your question, Vivek. So answer is that there is not much of a difference between grid computing and big data architectures. Okay. Does does big data solution require huge infrastructure? So good part about any of these infrastructures is they are scalable. What does it mean by scalable? If you don't have too much of demand right now, you just start with a single computer. Tomorrow, if you grow demand, you have more users, you add one more computer. You don't have to replace the software or have to do any other transfer of the data. These solutions automatically scale to the hardware. They start moving automatically the data to new computer and so on. Therefore, as and when your need is growing, you keep on adding more and more hardware, and as and when the need grows. General thumb rule is the moment you fill up your 75% of resources, double the resources. And that works really, really well. All right. So it does not require huge infrastructure on day zero. It all depends on your requirements. How to choose solutions like Hadoop or Cassandra? That is Harsal's question. Good. We will have a detailed discussion on it towards the end of the session. We will go through various available architectures, because by the end of session you will understand what are the various components of a typical big data solution and how to differentiate between one from another. All right? Because it's a very, very difficult question to answer, and lots of even the senior engineers fail to answer this question. Good, thank you, Harshal. We will go into the details later, but you keep on reminding me this, okay? So Nitika is saying, please explain the point number four. The point number four, this is a myth. Is it a so big data is sounds like a big myth and big buzzword. So it is little more, more popular as a keyword, but it has a huge implication also. Okay, the fact that organizations like Gartner, Forbes, and lots of people who predict future have realized that unless and until organizations are able to handle big data, unless they do it, they will not be able to make a progress in today's competitive world. Okay, so it's not really a buzzword. Now, Sweta's question is, when small business decide to go for processing of big data, good. They need to figure out their data pattern. Okay, they need to do a bit of a experiment and bit of a back of the envelope calculation, figuring out when are they going to have such a data in 2 years down the line that they cannot handle using a single computer or a single high-end machine. So we all should lose hope right now on hardware to increase suddenly. All right. So assuming that hardware is not going to change suddenly, the processor is not going to be peta uh, flops, as in petahertz. Right? We have giga, mega, giga, tera, and peta. So processor is not going to become terahertz suddenly. So assuming that computing resources are going to be similar, is your data after 1 year or 2 years down the line be so big that you cannot handle using one computer? Okay, in those cases you should immediately start thinking in terms of moving to big data architectures. All right, I hope I answered your question, Shweta. So, Nitika, have I answered your fifth point? Fourth point. All right. Now, these are the salary trends. Lots of people have asked me this question, even that I had a discussion. So, yeah, this is a quick salary trends. I did it on last weekend. I actually went through the salary trends of Indeed.com. You can go and check it yourself. I'm actually surprised that the difference between Oracle and Hadoop salaries is quite big, right? All right. So you can have a look at that. And also you can see that the demand of various softwares has suddenly gone down. Okay. So you can have a look at that. So those were job trends. These are the various big data products, or you can say solutions. So big data, you can say solutions actually. They are not really complete solutions. So out of this, we have Hadoop, which basically able to helps you in handling lot of all kinds of data. While we have Spark, which does not have any storage, Hadoop has everything. Spark has only the compute engine. Cassandra has storage, but uh, but mm, it's not great for storing uh, very unstructured data. Cassandra provides you tables where you can store any kind of data, whether binary or anything. But still, if you need more complete solution, probably you would go for Hadoop. But Cassandra is a database which does provide you the computing framework also. Now you have Google Compute Engine, where you don't have to install anything. You can start using from Google, and they will charge you on pay per computation basis. Number of number of CPU hours you consume, they will charge based upon that. Then you have MongoDB. MongoDB, similar to Cassandra, is good for storing data and doing basic computations. Okay. So Sweta's question is, this job trend analysis is also done through big data processing? I don't think so, because the number of jobs are hardly million records. Okay, so it's not that big a number. All right. Which one is better in terms of when you're comparing? Sweta is asking that which one is better. Um, okay. Harsal's question is Hadoop compatible with other engines? Yes. The fact that Spark can run on top of Hadoop and I mean yarn is structure. Similarly, on Cassandra, you can run MapReduce and you can access MongoDB's data from Hadoop. And Google Compute Engine also provides you map reduce paradigm. So Hadoop is actually quite compatible with Spark and MongoDB and Cassandra. So a lot of people actually assume that you would be having Hadoop infrastructure in place, and in case they are building a solution, they need to build around Hadoop. That is why Apache Spark made it possible to run Spark on top of Hadoop. All right. So which one is better in terms of big data solutions? That is Sweta's question. The answer is based on your requirements. If you require a more complete solution, then you go for Hadoop. In case you want to get your work done immediately and you don't want to install too many things, you just go with Cassandra or maybe MongoDB. Okay. And in case your data is smaller but your computing is complex, then you go for things like Spark. Or if you already have Hadoop infrastructure and you need fast computing, then you go for Spark. In case you don't want to take a headache of installation of any kind, you start using things like Google Compute Engine. And specifically, you've got money as well as you have got your data is not very serious. You are okay uploading the data to Google servers, then Google Compute Engine is okay. Hadoop versus Spark, we cannot compare because Spark is just a compute engine. So the way when we compare Spark against Hadoop is in terms of MapReduce. MapReduce is the compute engine provided by Hadoop. We'll talk about it in a minute. So quickly, Spark is doing pretty good job. So we will be taking a full session on Spark as part of 11 classes. Okay, where you will get a fair amount of hands-on idea on Spark. Yeah. Yes, Nitika. It means it will depend on our need. Tarak's question is, can you give live examples of where Hadoop and others are used? So, mm, okay, so Hadoop is used in case of any kind of data. So the way lots of organizations do is, who have realized that their data is going to become bigger anyway, they install Hadoop by default. They install Hadoop by default to store their general data, general files basically. And in case you are trying to store a lot of data from various devices, like then Cassandra would be good or HBase might be good. If you are storing a lot of complex data, such as the whole web page, then MongoDB might be good. And if you are doing a lot of computation, you will have to use things like Spark, say machine learning and all. And in case you are running a website whose data you can store happily on Google Compute Engine, then you'll go for Google Compute Engine. All right. So Huda's question is, which is good for mining big data? Okay. So, I mean, mm, the general, if you are doing a lot of data mining and your data is in terabytes, a, a composition of Hadoop along with Spark is good enough. Okay, we have Spark and Hadoop installed on our labs, so you can utilize those. While we don't have Cassandra and MongoDB on these labs, which are provided to you as part of this session. Okay, so yes, except for Google Compute Engine, everything else is open source. That is correct, Sweta. Mm, all right. What you have to use, yeah, what you have to use is based on your requirements. Right? Nitika, was I able to answer on how to decide which one to use? It's a complex answer. There are actually more solutions than you can imagine. Okay. And out of all the solutions, when I've studied, I found that Hadoop to be most complete out of it. Hadoop, in conjunction with Spark, is the pretty good solution for most of your problems. Yes, Lakshmi Narayan, you have a question. You have raised your hand. Vikas's question is, can we use Spark with Cassandra? That will be not a good solution. Reason being, Cassandra, Spark you will have to install the resource manager such as Mesos or Yarn to run Spark, because Spark cannot run on top of Cassandra. So you'll have to install it separately, and Spark will be reading data from Cassandra, which means there will be a cost associated with the transfer of the data. They have not done a very strong integration with Cassandra the way they have done with Hadoop. All right, that was Vikas's question. Sweta's question is, does Apache Hadoop has its own database? Yes, it's called HBase. It is good for millions of rows and millions of columns, or billions of rows and millions of columns. Below that data, you should be happy with your MySQL. All right. So Nitika is saying why Hadoop and so I was saying that Hadoop in conjunction with Spark does solve a lot of problems, because Hadoop seems to be the most complete solution out of all of the solutions available. If your requirement is just for a small project or a small, uh, you know, it's not something like a long term, then you go for things like Cassandra. If on an organization level, the most complete ecosystem as of today is Hadoop. So yes, Hadoop works as a database store also. Okay, that was Lakshmi Ryan's question. Vikas says, so shall I move data from Cassandra to Hadoop and then use? Yeah, that is how it will. So the way it works is Spark provides you way to read the data from any source, whether Cassandra, MongoDB, HDFS, not normal file system, anywhere, right? So Spark, you can tell that, hey, read my data from Cassandra. But the problem would be, in almost all distributed computing solution, we send the computing to the data, not the data to the computer. All right, the way we did in all these J2E architectures is, we had a database access layer where we access the data from remote computer, churn it, then do something about it, right? In all of these solutions, the data used to get transmitted. Here, in almost all big data solutions, we we send the code to the data. Okay, it's like sending the axe or sending the woodcutter to the wood instead of bringing the wood to the woodcutter, right? So if you have humongous data and you are transferring a lot of data over the wire, say you stored your data in Cassandra and you're trying to process it using Spark, then the whole purpose of computing is lost. Okay. So Nitika's question is why Hadoop is much better than others. I'll show you immediately after some time that Hadoop has got almost all the components in place. All right, we'll talk about it. So Spark is not having any database. It is just a computing tool which needs underlying database. That is very correct, Shweta. TJ's answer question is, can we please have more questions after some time? Yes, we'll have more questions after some time. Or you drop me an email and we'll have more questions. Okay. Yeah. All right. Now moving ahead. Now let's talk about Hadoop a little bit. So Harshil's question is good. He's saying that when you use a compute engine with Hadoop, does it impact network bandwidth? So in case the tool is not designed correctly, it will impact the network bandwidth. If the tool tries to get the data out of Hadoop, try to process it, and then does something, then it will basically do a lot of data transfer. But Hadoop provides mechanisms such that the tool which is running on top of Hadoop can give the code to Hadoop and say, can you execute it near the data? And Hadoop will do it happily for you. Okay. So in those cases, the network bandwidth will not be consumed. We'll go into far more details when we talk about Hadoop more, how these tools avoid usage of the network bandwidth. All right. Now, talking about Hadoop, it was created by Dog Cutting, who was working at Yahoo with Mike Caffarella. And when they were building their own search engine as their personal project, they realized that they cannot proceed unless until they try to do the same thing what Google did. Okay, so luckily for all of us, Google basically made their Google file system and Google MapReduce and Google Bigtable all of the papers describing in detail what are these tools. On the same lines, dog cutting implemented Google file system and it is now known as Hadoop distributed file system, and Google MapReduce became Hadoop MapReduce, and Google Bigtable became HBase. Okay, so he implemented all these three papers from Google, and that's how Hadoop was born. It was named after the toy elephant, which dog cutting son was playing, and it was open source. So probably why Hadoop is so successful is probably its licensing. It is open source, which means nobody can stop you from using it. And open source, that too Apache license. Apache license is something the most liberal license you can have. You can use Hadoop in your organization without having to worry about paying someone. Whether your work is professional, whether you are a healthcare company, you are NGO, or you are any corporate, you don't have to worry about paying somebody for using any Apache licensed product. Okay, and there is no obligation whatsoever okay, with respect to Hadoop. Now, it's quite supported, popular, and powerful. It's a framework to handle big data. And what does it mean? It means the framework, all the components that lie under the umbrella of Hadoop are supposed to handle big data. And what does it mean by supposed to handle big data? They are supposed to do reliable, scalable, and distributed computing. Reliable meaning if one node goes down, there is somebody else to do the work. Scalable means if we need to handle bigger load, we can add more hardware. And distributed means we can we can distribute a logic onto multiple multitude of computers and get it done. So all of the components, in the beginning Hadoop was three components, and right now there are around 14 components that lie under the umbrella of Hadoop. And all of these components have these three characteristics. Okay, and it's written in Java so that it can run on lots of devices. No other reason. Okay. Now Sweta's question is, how old is Hadoop? Hadoop is around four years old. Although the first implementation was, I think, done in 2009. Okay, but it 2009 or 10. So, but it became popular around 2011. Sweta's question is, does Hadoop has inbuilt computing engine? Yes, that is equivalent to GMR, which is Google MapReduce. It's called Hadoop MapReduce. That is their computing engine. What is Google File System? GFS. So Nitika, the GFS means Google File System, and GMR is Google MapReduce. Okay. Are there any versions of Hadoop like we have in JDK? Yeah. So there are multiple versions. Hadoop 1.0 was there, then Hadoop 2.0 has come, and now everybody uses Hadoop 2.0 for various reasons. We'll go into those details in the second session. Uh, Hi Ali. So Ali is saying that where do I download Hadoop package? So you can go ahead and either, if you have signed up with our session, you don't have to download much. You can straight away start using our ecosystem. In case you want to download, you can download probably either Cloudera's virtual machine or Hottenbox virtual machine. Okay. So we will, Nitika will go into the details of file system MapReduce quickly. No worries. Right. So Rania's answer question is, what is the output of Hadoop? So Hadoop is basically a place where you can store files. I will talk about it. Where you can store data, where you can run your queries and get the answers. All right. What is Hadoop ecosystem? We'll show. So this is Hadoop ecosystem. All right. So at the base of it, there is something called HDFS. HDFS is the main component on which every other component relies. Okay, HDFS is where you store the data. And why it is so special? Why did we have to create a new file system? Let's get into the details. So my question before I go ahead, let me ask you a question. If you had 100 terabyte of data, how would you store it? Let's say you are living in a hostel and all of you realize that, hey, let's build our 100 terabyte storage for storing our movies so that we can all store this our movies at central place and can watch it anytime we want. How would you build this? Do not answer it in the terms that we will buy storage from Amazon or Google. The answer is, how do you build such kind of a storage? Yeah. So it's a question to you. If you have to store 100 terabyte of data, how would you build this kind of storage? Anyone quickly? I'll wait for maybe 2 minutes. Okay, Rania says that based on file system concept, good, good. Tarak says network multiple system of say 5 TB each, good, excellent. Shweta says by buying hard disk, yes, that's correct. But buying how many hard disk and how do you connect them? Nitika says tables and in tables, all right. But in do you want to store your movies in tables? Then every time users who want to play a movie, they will have to, because VLC player will not play the data from play the movie from a table, right? TJ says one indexing system that will say where actual data is present. Good. Go ahead. Go ahead. Yeah, I want to see that. Pop says that store in many sources. Good. Many sources as in like what? Sanjay says has to be distributed multiple nodes, one node for standardization. Good. Uh, Vikas says we will distribute the storage on each member computer and then make a central program to search on each system. Excellent. Divide data into clusters. Yes. Bring each computer in one network and let each one store some movies. Good. That is Vivek. TJ says pointer from indexing system to data store. Okay. Okay. Yes. Nitika says then file system. Correct. And Lux says buying hardware and storing file and segment. Excellent. So almost all of you are on the lines. Some little bit ahead, some little bit with me here. So this is how we did it. Long back when we had to store terabyte of data, this is how we did it. Although you might say that Huda says distributed DB and others DB. Yes, Huda. So I want to, before we jump to that place, I want to go organically one step at a time. All right. So before this whole new set of databases, new set of file system came, this is how we did things. And trust me, lots of people still do it the same way. When I was working with these people, some people from NASA national labs, they were when I was talking to them, they still use the file system to store the geographical informations. All right, and they had a similar solution right now also. So this is how we did. What we did earlier was we'll buy 100 terabyte, 100 hard disk, each of 1 terabyte, and make connect these hard disks somehow into these computers. Say we have 100 computers, or maybe 10 computers, each containing, or maybe say 50 computers, each containing two hard disks in each, and then connecting them together, right? Such that they are available in the network, and once they are available in the network, we mount these or map these to folders. So on maybe 5 computers we have this main folder, each containing main folder, and under this there will be 100 folders representing drive 1, drive 2 up to drive 100. Now we can start storing the movies inside drive 1, drive 2, drive 3, drive 4, and so on. Now the question is, do you see any problems with this stuff? So what you got out of this kind of exercise is a big folder called main folder. Under that folder, you got 100 folders, each representing one hard disk somewhere around the network. Now you are free to store your data in these four subfolders. So question is, do you see any problem with this architecture? Shweta is saying searching is a problem. Correct. Correct. Vikas says yes, if one PC goes off, then whole network goes down. So um, let me, that's why I was saying that same mapping we have done on other computers also, and we have told all the people that these are the five computers that contain this mapping. Okay, but if one computer goes down, maybe one drive goes down or two drives will go down. Okay, so you are partly correct. Yes. Gangadhar says that searching will be issue. Correct. Sanjay says too many files may be efficiency problem if you need large number of folders for one query. Good, good. So distribution of data will be a problem. Pop says that if we have too many folders, we may have difficult time to find a particular data. That's correct. Problem in accessing. That is right. Yes. Any other problem do you see, Nitika? I agree completely. The searching is going to be a problem. Good, good. So we talked about few things. Almost, I think we have covered almost all. So these are the general challenges in this architecture. Yes. Thank you, Nikhil. Nikhil's point is saving new data in appropriate folder, which is equivalent to finding the searching for the place which is available. Right now, imagine that we could have built a scheme that all the movies from A go into one full drive 1, B go into drive 2, and so on. That scheme will keep on failing all the time. And hence, as you all have pointed out, that searching or storing of the data will be an issue, right? Now, if you have 101 terabyte drives, so these are the challenges you will see. First is failover and backup. You might argue that below each drive, we will put one more drive and we'll make it RAID 1 and we'll have a backup on the same computer. But the problem is not only in the hard disk, the problem is also in case one computer goes out of network, your data is lost. Trust me, there are mouse in there are mices in the data center which might cut the cable. There are hundreds of different kind of network problem. There are operating system which might be having problem. There are other problems because of which each computer is prone to failure and goes out of network. So even though you might be having a backup on the same drive like a RAID 1, but in case your node goes down, the whole data is lost. Next is the data is not distributed uniformly. Is this the best value for money? Is this the best value for of resources? You might be having already 500 GB, 200 GB disks. The more disks you will have, the bigger problem you will have in this architecture. Now, what about increasing accessibility? This is something. Yeah, that's correct, Rania. The fault tolerance is pretty low in this one. And increasing accessibility. Imagine that a new movie came yesterday and all of the people in your hostel have to watch the same movie. The hard disk is a physical thing where the header moves from one place to another. It cannot serve more than few users at a time. And therefore all these users will have to wait to watch the movie. You got the point? So because all of we will be storing same movie on the same disk, and all the users will have to access the same disk to watch a movie, right? Therefore it will be heavily slow. And even though our 99 computers are sitting idle, one computer is being thrashed because of the load, because this movie is new, lots of people want to watch this movie. All right. Next is scaling out. Today we realize it's 100 terabytes. Tomorrow we might need 150 terabytes. Is it good enough to scale? As in, if we just buy more hard disk, is it okay? Is it easy to distribute data automatically, or do we have to change whole of our scheme and we have to handle a lot of more things, right? So these are the problems you will face in this. So what do you do then? That's where the HDFS comes into play. All right. So how does HDFS do it? In HDFS, there is admin node and there are data nodes. Data nodes store the actual files, while admin node store the index of what is where. As all of you have pointed out already, that searching will be an issue and we need to keep a central node where we'll store this information, which file is where. That's what goes into admin node. Admin node is a single machine, while there are multiple nodes in the network. Now, so admin node behaves like a metadata, and all of these things, admin node and data node, are nothing but processes. So we are discussing what is Hadoop distributed file system. It has two kind of nodes. There is a singular node, which is a central node called admin node or name node, and there are multiple nodes which are data nodes. Data nodes only store data, while admin node just keeps a note of what is where. Okay. Sweta's question is big data always about metadata like processing old business data, or is it's for both? Sweta, it's for both, right? And we'll talk about these things in detail again. Now, so you get it? If we lost all the data that was in admin node, what all things will be lost? Anybody? If our admin node goes down, all right. So actually, we will lose a lot of everything. We'll go into your answers again. And so each HDFS for unstructured data or HBase is for structured data. Yes, you can say that, Sweta. That's correct. HDFS is for generally unstructured data and HBase is for structured data. Now, Lux says that do we need to have the data duplication distribution different node also? You will see that quickly after some time, Lux. All right. So yes, Tarak says that in case we lose the admin node, all the pointers to the data will be lost and hence everything will be lost. Okay. Nitika says nothing will be lost. It looks like nothing will be lost, but actually we lost the mapping of where are our files, and therefore we'll go into the details more. Yeah. All right, we'll go into okay. Let's avoid this right now. So we have HDFS. HDFS has an admin node and data node, and further, the data, the way it is stored is each file is sliced into chunks. Earlier it used to be 64 MB, but now it is each chunk or block size is 128 MB. So if you're trying to store a movie of 1 gigabyte size, it will be broken down into 8 blocks and then stored into multiple data nodes. Okay, this helps us fitting big files into small disks. Also, it leaves less unused space onto the disk. It optimizes the data transfer. It distributes loads to multiple machines. So, if a person is watching a movie, first first part it will read from one data node, second from second, and so on. That way the load is distributed to 8 node instead of one node. All right, all right. So this is how the blocks work. Now further to it, each data node has multiple copies. All right, each block in data node, so we talked about a file is broken down into blocks. Each block of the file is replicated multiple times. The replication factor is generally 3, which means each block is 3 times copied, and hence if you are trying to store 100 terabyte, it might take 300 terabyte, but that's a trade-off. And also you can tune it, you can change replication factor from 3 to 2 or 1, but that's too risky. Okay, so avoid setting replication factor of 1 at every cost, because since the data is sliced into blocks and one node goes down, the chances are that this node would be storing the blocks for thousands of files, and therefore all those thousand files become useless because they lost one part. If these files had only one replication, then all of these files will go useless. Therefore, the replication factor is generally capped like 3, not too much, not too low, 3. This will help us, this helps in a very organic, or you can say that in a very robust backup system. So what happens, that say one data node goes down, all the blocks that got lost here, they will be having two more copies left somewhere else, and quickly it will, the other nodes will be informed to take a backup copy of this one, so that the replication factor again reaches 3 from 2. We went to the moment we lost one data node, all those blocks which got lost, the file belonging, they will have now a replication factor of 2, and suddenly it has to be rebalanced to again 3, which was promised to the end user. So each file, each block of a file is copied 3 times into different machine. No two copies of a block stay on the same node, they have to be on different nodes. All right, so that is how it works. Now, you might see that the typical way that, okay, there will be a user will come and talk to the name node or admin node, and admin node will read the data from data node. No, it's not this way. Otherwise, name node will become the bottleneck for the whole game. The strategy is like this. User talks to HDFS through a library or a driver. The driver goes to the name node. Name node tells driver that go to data nodes and read the data by yourself. Do not bother me. Okay. Name node just tells it that these are the blocks. These blocks are existing on these data nodes. You go there and read it by yourself, and driver reads that for you and gives it to you. All right, and driver makes it look like it's a nice beautiful file system, and that's the role of the driver. All right. All right, so is torrent an example? Yeah, the whole system has been designed like a torrent system. Okay. Are copies on separate nodes? Yes, that's correct. Are there multiple drive nodes? Multiple drive nodes? No, there is not multiple driver nodes. There's so driver is not a node. Okay, this is not a node. It's just a library. It's like command. It's like a ls command, or it's like a, um, a command, right? It's like a file system driver. It is not a server. While name node and data node are processes listening on like a network service, they are always running. Okay. Yeah, you can think of it like a API. All right. So yeah. So user, let me explain Nitika again. User uses this library, or you can say command line tool called client or a driver. If you are a Java programmer, it will provide you a Java API. This client will talk to the name node. You will tell client that, hey, this is the name node. Can you talk to it and get me the data? It will talk to the name node. Name node knows that where is your data, gives back the, you will ask name node, the client driver will ask name node that can you give me the information about this particular file, and name node replies that this file has got these many blocks. This block is located on this data node. This block is located on this data node, and so on. This client driver assembles it for you and gives back to you. So this client driver will be running on the same machine as you, connecting to name node via network port, and then giving back the data to you. All right. Is that clear, Nitika now? All right. So now you have this HDFS architecture. Again, the same diagram. You have name node. Name node contains metadata. Client talks to name node, gets the metadata, and then gives out this. Okay. Now, same process has been described here. Client talks to the, this SDFS client or driver talks to the file system, gets the name node. Name node gives back the. So here we are trying to write the data. So before writing the data, the request goes to the name node that I'm trying to write this file. Name node blocks a place for you here, and at the same time, you go to the data, and name node tells you that go to the data node and store the data. Your client library will directly talk to name node and store the data there. And once it's done, it will inform name node that, hey, I am done with saving the data, and can you confirm? And then name node will say, okay, fine, this file has been written successfully. And that's all. Now, unless and until, in case HDFS client while writing data to data node dies out, in those cases, the file in the name node will not be, successfully committed. All right. So this is similar way. The general idea is that we should not be routing everything through name node. Name node has to be fairly free. Okay. And the kind of information name node stores is the file name, user records, blocks as in part 1, part 2, part 3, how many, what is the replication, and what are the data node containing that information, and so on. All right, moving on. So is this clear to everyone? Yeah, no, not clear. So in what format the data is stored on name node? Name node keeps the file as a file locally as well as in the memory. All right. So name node keeps all of the data in the memory and supported by the disk. In case name node goes down, there is something called secondary name node as a backup, which is, you know, a passive backup, as in there is a mirror image of name node which will have exact same data what name node has, but will never be used until name node goes down. The moment name node goes down, secondary backup takes the place immediately and you can use. Yes, Sanjay, that is a very correct analogy. Name node mainly has metadata and transaction log, so it's like MDM solution for HDFS. That's correct. All right. In case you are okay with our file system, you should try out this kind of command. It will show you exactly where all the blocks are stored. On each data node, the data will be stored as small files, each of size 128 MB, except for the last part. Last part will be generally smaller than 128 MB. So a quick overview. I know I am running around 10 minutes late, but uh, every question needs to be answered, and therefore sometimes because of the questions. All right, so let me just take you through this quickly. So on the top of HDFS, we have HBase. HBase is a NoSQL database which runs on multiple machines. It stores its data onto HDFS, and there are multiple things HBase provides. If your data, the data you want to store is in the form of tabular, is a tabular format, then you use NoSQL data. All right. In case and then you have this computing engine called yarn. Yarn basically, you have this compute engine called yarn. Yarn basically makes it possible to run anything on multiple computers, and that is why MapReduce uses yarn to execute maps and reduces, Spark uses yarn to execute its logic, and so on. There are more than 15 components which run really well as a compute engine on top of this HDFS. All right. So since we have already multiple nodes running on HDFS, it will be beneficial for us that if we distribute our logic such that the data is not transferred across the network, instead we are running the logic near to our data. That's the role of yarn in the game. All right. Then we have Hive. So a lot of work can be done using SQL. If there is somebody, please note that HBase does not provide you SQL like query. Instead, you use Hive, which can query HBase, which can query your normal CSV file or tab separated file located in HDFS, and so on. Similarly, similar to Hive, we have Pig Latin, which is similar to Hive in the sense that it looks like SQL, but it is more designed for distributed computing. Okay. Then you have Mahat. Mahat is bunch of libraries which basically provide you machine learning and statistical analysis of the data. Recommendation is one typical example. Other than that, classification is another. There are a lot of functions which Mahat provides you. Then you have Uzi. Uzi is basically combines all of these tools together. It's like your Apache Ant, or you can say Makefile, or you can say Maven. So when you have a big project, some of it will be importing data, other will be running on HBase, Hive, and so on. So if you have to run the whole project, you will compose your Uzi XML and then run it. You have Flume and Scoop. Flume is to import data from various file systems or from various resources onto HDFS, while Scoop is for transferring data from structured sources such as databases into HBase or into HDFS. All right. So that's about the whole ecosystem of Hadoop. In case you want to go ahead with our sessions. So tomorrow, which is what is the date? 19th April. Okay. So you can sign up for this class from tomorrow onwards. It has only got 3 seats left, so you might have to go for another session, which is starting on 25th April, and that will be 7 a.m. IST. All right. So that was a little bit about Hadoop. Let me go through. So please use Cloud Labs if you are already signed up with us. And this is the assignment. Okay. Please log in into Ambari console. I'll show you that. Okay. The login password would be there in the okay in the installation document. So no big data. Under my courses, you will see this one. And each session you go through here the installation instruction. Do you see the installation instruction? Okay, you click on open. It will have all the details about how to install and how to access the Cloud Labs. I do not want to open it because it would have the password. I do not want to share it right now. Okay, so finish this quiz which is there. Half of the quiz you can finish now, half of the quiz you can finish after tomorrow's session. Okay, we, we this quiz composes both, and we will upload all the recordings just like this one. These are the old recordings. Also finish the regular expression session. This will be very very useful, and you will be really benefited out of it. Also the Java session is available. You should start finishing your Java session. Okay, that you might find it useful. All right, so this is your sessions, and in the meantime this is our cluster. It shows what is up, what is down. Right now right now you can see that secondary name node is up, secondary name node, which is a backup, is down, which we have intentionally shut it down, and so on. Okay, so you can see the cluster, and if you want to operate upon HDFS, you will see that. We'll go through all of these tomorrow in detail, how to and go into the more details about Hadoop ecosystem. All right. So for tomorrow onwards is a paid session. Only the today's one was free for all. Okay. And yeah, I think I've covered it. All right. Any questions for me? All right. I know you must be running late for today, and yeah, I know. So yeah, all those candidates who have already enrolled, they don't have to worry. Okay, and there are only actually 3 more seats left for this session, so you might have to. This one is almost full. Okay. So if you want to go ahead with the full session for these, there are 11 classes, and yeah, the 11 classes we'll go through. Probably this is the most complete course on any big data solutions out there. Other than other than these all components, what we have here, we'll cover all of these, plus we will cover Spark, and also we will cover something called Zookeeper, which is probably the most commonly used tool. Okay, good. All right, so see you tomorrow and stay in touch. Even if you're not enrolling, stay connected, and be active on our forum. We make sure that we answer the questions correctly. Okay, we have a forum on our website. If you register, you can just sign up there and you will see this forum, and then you can have that. All right. All right. So feel free to, if you have any questions related to our Cloud Labs or any question related to the course, any technical question, you send a mail to Hadoop at No Big Data. In case you have any questions related to the course schedule or the planning of the course, you can write mail to reach us at No Big Data, reach us at No Big Data, and that should be good. Okay. So thank you very much. All right. So if you have any question, this is my personal email. I have a phone number. You can call me, but my phone is generally out of reach because of the network issues. So the place I live has got a really bad network. So prefer this number instead. Prefer these numbers instead. Okay. Okay. So feel free to stay connected. Great. I'm happy, Ravidas, that you find the session really useful. And Sanjay is saying, will we have daily homework or will it be once per two classes? Generally, we will have daily homework, Sanjay, and but it's okay if you are submitting it little later. Okay. Amal is saying all sessions will be online. Yes, all sessions will be online. No, there are yeah. There's not much of a time between Saturday and Sunday. I know very well. So try to do the free this the objective questions should not take more than 10 minutes to finish. Okay, these are around 30-40 questions. That should be good. Thank you, Malvika. I'm happy that you like the session. Okay. Hi Bob. See you tomorrow. And okay. Hi Vikash. I'm happy that you find it great. Hi Lux. Thank you for your valuable time as well. Shweta, thank you very much for being part of it. Thank you, Diego. Thank you, Sriram. Yeah, all of you will get recordings and slide as well. Sanjay, I think you are already signed up, so it will appear here for you. Under my courses, you will see session one, and you will see the recording here. Okay. For rest of the people, we'll send the email as well. Okay. You might get both actually, Sanjay. And hi, Nalini. I'm happy that you find it useful. Yes. Please feel free to call me on this number. All right. And yeah, or drop me a number, I'll call you back because I have a little bit network problem. Okay. Rania, thank you very much for being part of the session. Niti, I'm happy, Nitika, that you like the session. Okay, great. I tried to answer your queries. I must have missed somebody's questions, so feel free to drop us an email at reaches at no big data. I make sure to go through each and every question and answer every one of those. All right. So yeah, I'm just making a note of your number. Yeah, great. I look forward to further interaction. I'm sure I'll make it interesting. I'll try my best to make the whole sessions interesting, and every next batch is better than the previous one. All right. So we try to work hard on this. So stay in touch, stay connected, be active on the forum, and keep learning. All right. All right. Thank you very much. Stay connected. Bye bye. I'll have to hang up now. Bye, Abhishek. Bye, Minu. Bye, Rania. Bye, Vikas Mishra. Bye, Malvika. Bye, George. Bye, Bruce. Bye, Sonali. Bye, Huda. Bye, Subramaniam. Bye, Preeti. See you later. Bye, Jay. Bye, Amal. Bye, Harshal. Bye, Karthik. See you, Sayed. Bye, bye, Vivek. And bye, Sanjay. See you tomorrow. And bye, Nitika.